Welcome. There is nowhere to be and nothing to do now, only this voice and the dark behind your eyes. Let your shoulders drop into the mattress. The word empire began quietly, long before flags or crowns, in the Latin imperium, meaning the power to command. It described authority itself, not land. Over centuries, that single word grew to hold entire worlds. Rest here, in the slow unfolding of that history. The Akkadian Empire is considered history's first empire. Around 4,300 years ago, a ruler named Sargon united the city-states of Mesopotamia under one throne. Villages that once quarreled over water and grain suddenly answered to a single distant voice. Clay tablets recorded harvests and laws in careful, wedge-shaped script. It was the first time so many different peoples were held together by one government. Tower. The Persian Achaemenid Empire pioneered administrative provinces called satrapies. Each region kept its own customs, its own language, even its own gods, while a governor answered to the king far away. Messengers rode along royal roads, changing horses at stations built just for speed. It was an early experiment in ruling difference without erasing it. Order and diversity, somehow, learned to share the same empire. The Roman Empire used a road network to project power across continents. Stone paths stretched from misty Britain to the sun-baked edges of North Africa. Soldiers marched along them, but so did merchants, letters, and ideas. Some of those roads still lie beneath modern highways today. A civilization learned that control could travel exactly as far as its roads could reach. The Mongol Empire was the largest contiguous land empire in history. Under Genghis Khan and his descendants, mounted riders crossed step after step until their reach touched two oceans. Trade routes, once fragmented, became a single vast corridor connecting east and west. Silk, spices, and ideas moved faster than they ever had before. For a brief, remarkable stretch of centuries, one bloodline's shadow lay across most of Asia. Empires historically expanded through conquest, trade, or religious spread. Armies won some territory outright, while merchants quietly wove other lands into economic webs. Missionaries and monks carried belief systems across borders that soldiers never crossed. Each method left its own kind of footprint on language, architecture, and memory. Power, it turns out, has always traveled by more than one road. The British Empire once controlled a quarter of the world's landmass. At its height, the sun genuinely never set on it, since some part of its territory always faced daylight. Ports and colonies stretched from icy Canada to tropical India to the shores of Australia. Maps were redrawn in shades of pink across every continent but one. It was, for a time, the widest reach any single government had ever held. Historians define empire as centralized rule over diverse conquered peoples. It is less about size than about structure, a single authority holding together many different cultures, languages, and laws. Some empires ruled gently through local elites, others through direct control and garrisons. What united them was the simple, persistent question of how to govern people who never chose to belong. That question has echoed through every age since. Communication delays historically limited how far an empire could effectively govern. A message from Rome to its farthest province might take weeks to arrive, and weeks more to return with an answer. Decisions were often outdated before they ever reached the people they concerned. Distance, more than armies, quietly shaped the true size of any empire. Even the mightiest throne could only stretch as far as its fastest messenger. The fall of empires often followed overextension of supply lines. Armies stationed too far from home grew hungry, isolated, underpaid. Grain that once flowed steadily from conquered lands slowed to a trickle, then stopped. Borders that had seemed unbreakable simply grew too thin to hold. History suggests that empires rarely collapse all at once. They unravel slowly, thread by distant thread. Let the breath lead you now, in and out, without any effort attached to it. Feel the inhale rise like a slow tide, then let the exhale stretch a little longer than before. There is no rhythm to keep except this one, unforced, unwatched. With each release of air, let your shoulders sink a fraction deeper into whatever is holding you. Nothing needs to happen next. The breath already knows the way down into rest. The Milky Way galaxy contains over 100 billion stars. Each one is a sun in its own right, many with worlds circling them in the dark. From here on Earth, we see only a faint band of light across the night sky, a river of countless distant fires. Most of those stars have never been named, only counted in vast approximations. The galaxy holding us is, in truth, an ocean of light too large to fully picture. 100,000 light-years across, that is the width of our galaxy. A beam of light, the fastest thing there is, would need that entire span just to cross from one edge to the other. Our solar system sits far from the center, tucked into one of the galaxy's quieter spiral arms. From edge to edge, the Milky Way is wider than almost anything the human mind is built to hold, and still, it is only one galaxy among many. Earth orbits the Sun once every 365¼ days. That small extra quarter day is why, every 4 years, a calendar gains one more day to stay in step with the sky. Our planet moves through this loop at tremendous speed, though we feel none of it standing still. Season follows season because of this single unhurried circuit around a star. It has repeated, uninterrupted for longer than any human memory can reach. Light from the sun takes about 8 minutes to reach Earth. That means the sunlight warming your skin on any afternoon left its source 8 minutes earlier, already traveling before it ever touched you. If the sun somehow vanished this instant, our sky would stay bright a little while longer, unaware. Every sunrise is, in a small way, a message from the recent past. It is one of the gentlest reminders that light itself takes time to arrive. 4.24 light-years away lies our nearest star system, Alpha Centauri. That distance sounds small compared to the galaxy's full width, yet it would still take our fastest spacecraft tens of thousands of years to arrive. 2 suns and a smaller red companion form that neighboring system, glowing steadily in our southern sky. It remains the closest star beyond our own, and still it is unreachable within a single human lifetime. Distance, even to our nearest neighbor, humbles every sense of scale. Voyager 1 is humanity's most distant human-made object. Launched decades ago, it now drifts far beyond the planets, carrying a golden record etched with sounds of Earth. No spacecraft has traveled farther from home, and none has done so with such quiet purpose. It continues onward, silent and steady, into space that has never known another human trace. In some sense, it is our furthest reaching hand, extended into the dark. Voyager 1 has traveled less than 1 light day from Earth after 45 years. Despite decades of steady flight at astonishing speed, it has not even crossed the distance light travels in a single day. That single fact reveals just how vast the space beyond our solar system truly is. Its faint radio signal, moving at the speed of light itself, still takes many hours to reach home. Even our boldest journey so far is only a first small step beyond the doorway. The speed of light is the universe's fixed cosmic speed limit. Nothing carrying mass or information has ever been observed to exceed it, no matter how much energy is applied. This single number, measured precisely, shapes how galaxies, stars, and even time itself behave. It is not simply fast, it is the boundary condition of reality as we understand it. Every distance in space, in the end, is also a measure of time. Special relativity forbids matter from traveling faster than light. As anything with mass approaches that speed, the energy required to push it further grows without limit. This is not a matter of better engineering or more powerful engines. It is a structural feature of spacetime itself. Physics allows massless things, like light, to move at that limit, but nothing more. It is one of the quiet, unbending rules the universe has never once been seen to break. Crossing between stars would demand patience beyond ordinary imagination. Even at a fraction of light speed, a journey to the nearest star system would outlast the lifetime of anyone who began it. Ships would need to carry not travelers but generations, each one born and raised inside the hull. Centuries would pass for every single hop between suns. Distance, in this sense, is not just miles but unbroken spans of human time. Let your body grow heavier now, resting fully into the surface beneath you. Feel your feet first, warm and unmoving, sinking a little deeper with each breath. Let that heaviness rise through your legs, through your hips, settling like sand into stillness. Your shoulders lower, your arms grow still, your hands forget the need to hold anything at all. Even your head feels supported, cradled, unwilling to lift again tonight. Between 1969 and 1972, human beings walked upon another world. 12 astronauts stepped onto the moon's gray dust, leaving footprints that remain undisturbed to this day. Each mission carried its own crew home safely, a feat of engineering built from slide rules and careful hands. They collected stones older than any structure on Earth. For a brief handful of years, our species touched a world beyond its own. Since the year 2000, human beings have never left the International Space Station empty. Crews rotate through its corridors in a continuous relay, floating past windows that frame the whole turning Earth. For more than 2 decades, someone has always been awake up there, tending experiments, watching sunrises come every 90 minutes. It is the longest unbroken presence humanity has ever kept beyond its home planet. A small, steady outpost, circling quietly above everything we know. By the early 2020s, astronomers had confirmed more than 5,000 worlds beyond our solar system. Each one was found through careful, patient observation, a dimming of starlight or a telltale wobble in a star's motion. These distant planets range from scorched giants to small rocky spheres, not unlike our own. The count grows steadily month by month as new instruments sharpen their gaze. Every confirmed world is a quiet reminder that our sun was never the only one with company. The Kepler Space Telescope spent years staring at a single patch of sky, watching for the faintest flicker of light. From that unwavering gaze came thousands of candidate worlds, hidden in the tiny shadows they cast as they crossed their stars. Kepler did not travel far from Earth, yet it reached farther into the galaxy's population of planets than any mission before it. Its data still yields discoveries today, long after its instruments went silent. A small telescope, fixed on one corner of the sky, revealed how crowded the galaxy truly is with worlds. Proxima Centauri b circles the nearest star system to our own, a small rocky world bathed in dim red light. It sits close enough to its star to receive warmth, tucked within a region where liquid water might survive. No spacecraft has ever visited it, and none currently could reach it within a human lifetime. Still, of all known worlds beyond our solar system, none lies nearer to Earth. It orbits a star whose light left it only a little over 4 years before reaching our eyes. Around every star lies a narrow band of orbital distance where water could remain liquid rather than freezing or boiling away. Too close, and oceans vanish into vapor. Too far, and they freeze solid beneath endless ice. This region, often called the habitable zone, shifts depending on how bright and hot the star burns. It is not a guarantee of life, only a possibility, a window, where conditions might allow something like it to begin. Small red dwarf stars burn far more slowly than our Sun, stretching their lives across trillions of years rather than billions. Some of the exoplanets discovered so far circle these dim, patient stars, receiving a soft red glow instead of golden daylight. A world orbiting such a star could, in theory, remain stable for a length of time longer than the current age of the universe itself. Their light is faint, their warmth modest, but their endurance is extraordinary. Longevity, it seems, sometimes favors the quieter stars. In 1961, an astronomer named Frank Drake wrote a simple equation to estimate how many civilizations might exist that could communicate across the stars. It weighs factors like the rate of star formation, the fraction of planets that could host life, and how long a civilization might survive to send a signal. The numbers going into it remain deeply uncertain, more guesswork than measurement. Still, the equation gave scientists a structured way to think about a vast unknown. It turned an overwhelming question into a series of smaller, more approachable ones. A puzzle called the Fermi paradox sits at the center of the search for other worlds. It asks a simple thing: if the galaxy holds so many stars in so much time, why has no sign of another civilization ever reached us? Named after physicist Enrico Fermi, who raised the question over lunch in 1950, it remains unresolved. The silence itself has become part of the mystery. For 6 decades, an effort known as SETI has aimed radio telescopes toward the stars, listening for a signal that might mean we are not alone. It began in 1960 when astronomer Frank Drake pointed a dish toward 2 nearby stars, hoping to catch an artificial pattern hidden among natural noise. Since then, larger arrays and steadier receivers have joined the search. The sky has stayed hushed, but the listening continues. Somewhere beyond these walls, a low hum rises and fades, a furnace settling, wind moving past a window, a house easing into night. Sounds like these arrive without asking anything of you. They swell for a moment, then recede, the way tides pull back from the shore. There is no message in them to catch, only presence, arriving and leaving again. Let your body settle the same way, sinking into the mattress a little more with each breath that leaves. Despite 6 decades of dedicated listening, no confirmed signal from beyond Earth has ever reached a receiver. Telescopes have caught bursts, pulses, and strange flickers, and each has, in time, found a natural explanation: a spinning star, a passing satellite, an ordinary quirk of physics. None has held up as proof of another mind out there. The search itself has produced no false trumpet call, only years stretched across decades. Physicist Nikolai Kardashev devised a scale in 1964 to sort civilizations not by culture or history, but by how much energy they command. It divides advancement into tiers, each representing a leap in the sheer scale of power a society could draw upon. Where a civilization falls on this scale says little about wisdom or intent. It says only how much of the universe's energy has been put to use. The first tier on this scale, a Type 1 civilization, would make use of all the energy available on its home planet. Sunlight, wind, heat trapped within the crust. Every accessible source combined. Humanity today draws on only a portion of what Earth offers, still far short of this threshold. Reaching it would mean a world working in near total harmony with its own resources. Beyond that lies a Type 2 civilization, one capable of harnessing the entire output of its home star. Such a society might surround its sun with vast collectors, or divert its light through structures larger than a planet. No world has approached this level. It remains a marker on a chart, a measure of scale rather than something yet built. At the farthest reach of the scale sits a Type 3 civilization, one that commands energy on the scale of an entire galaxy. This would mean drawing power not from one star, but from billions, spread across 100,000 light-years. No observation has ever hinted at such a thing existing. It stands as the outer edge of imagination applied to physics. Freeman Dyson, a physicist working in the 1960s, proposed that an advancing civilization might eventually build structures large enough to capture a star's entire energy output. He suggested that instead of searching only for radio signals, astronomers might look for the waste heat such structures would radiate into space. It was a different way of framing the question, not just listening, but watching for the fingerprints of engineering on a stellar scale. To capture the whole of a star's light, a structure called a Dyson sphere would need to enclose it completely, wrapping the star in a vast shell of collectors. Such a shell would need to withstand enormous pressures and span a width far greater than any planet's orbit. No civilization, so far as anyone can tell, has built anything close to this scale. It remains a thought experiment stretched across the size of a solar system. Across decades of dedicated astronomical surveys, no confirmed Dyson sphere candidate has ever surfaced. Telescopes have scanned countless stars for the telltale infrared glow such a structure might leave behind. A handful of curious signals appeared briefly, then were explained by ordinary dust or stellar behavior. The search continues, patient and ongoing, but the sky so far offers only silence on this particular question. Project Orion, a design conceived in the 1950s, imagined propelling a spacecraft using small nuclear explosions detonated behind it. Engineers pictured a heavy pusher plate absorbing each blast, riding the shock waves forward like a boat riding successive waves. The concept promised extraordinary speed for its era. It was never built for spaceflight, but the blueprints remain a striking artifact of that ambitious decade. Nuclear fusion propulsion, despite decades of laboratory effort, remains theoretical for any voyage between the stars. Physicists have coaxed brief fusion reactions in controlled chambers, but sustaining one to drive a spacecraft is a far harder task. The energy such an engine could release would dwarf anything chemical rockets provide. For now, it exists mostly in equations, diagrams, and careful hope. Let warmth begin somewhere small, perhaps at the center of your chest, a low glow spreading outward like light through a closed hand. Feel it move into your shoulders, loosening what the day left tightened there. It drifts down through your arms, pooling faintly in your fingertips. It settles into your hips, your knees, the soles of your feet, until the whole body rests inside its own warm tide. The Bussard ramjet, a concept from the 1960s, imagined a starship scooping hydrogen straight from the thin gas drifting between stars. A vast magnetic funnel would gather this fuel and feed it into a fusion engine, powering the ship without needing to carry its own reserves. The idea remains elegant on paper. Whether such a scoop could work at real interstellar speeds is still an open question in physics. Generation ships would carry crews whose children and their children's children might be the ones to finally arrive. No single traveler would see both departure and destination. Entire lives would unfold inside corridors and gardens built to last centuries. Such a vessel would be less a machine than a small, self-contained world, carrying its own history forward through the dark between stars. Cryogenic hibernation, the long sleep so often imagined for deep space travel, remains unproven by any science today. Researchers have slowed metabolism in small animals for short periods, hinting at possibility. But safely suspending a human body for years, then waking it intact, has never been demonstrated. The idea endures mostly in fiction, waiting for biology to catch up with imagination. Breakthrough Starshot, an initiative launched in recent years, proposes accelerating tiny light sails using banks of powerful ground-based lasers. Each sail would be no larger than a hand, thin as a soap film, yet strong enough to catch a beam of concentrated light. The goal is to send such a craft toward a neighboring star system. It remains an early idea, tested only in small increments so far. A light sail, pushed steadily by focused laser light, could in theory approach a meaningful fraction of the speed of light. Unlike a rocket, it would carry no fuel of its own, relying entirely on the push of photons from behind. Reaching such velocity would still take years of sustained acceleration. The physics allows it, though no craft has yet attempted the feat. Antimatter propulsion stands as the most efficient fuel theorized, releasing more energy per gram than any other reaction known to physics. When matter meets its antimatter counterpart, both vanish completely, converting entirely into energy. Even a small amount could, in principle, drive a spacecraft across enormous distances. The reaction itself is well understood. What remains far out of reach is producing enough antimatter to matter. Producing antimatter in quantities large enough to fuel a starship lies far beyond anything current technology can achieve. Particle accelerators create it now only atom by atom, at enormous cost and energy. Storing it is its own puzzle, since contact with ordinary matter destroys it instantly. All the antimatter humanity has ever produced could not power a single light bulb for more than a moment. The distance between the physics and the engineering remains immense. General relativity, the theory Einstein completed in 1915, permits a strange shortcut through space-time called a wormhole. Picture two distant points in the universe connected by a bridge, a tunnel curving through the geometry itself rather than across open distance. A passage like this could, in theory, join galaxies separated by unimaginable spans. The mathematics allows it. Whether nature ever built one is an entirely different question. No wormhole has ever been glimpsed by any telescope in any survey of the sky. Astronomers have searched for gravitational signatures a wormhole might leave behind without success. Every observation of deep space, across decades of careful looking, has turned up nothing resembling one. The idea remains elegant on paper, untouched by evidence. For now, it belongs to theory alone. Miguel Alcubierre, a physicist working in 1994, proposed a way to bend space-time itself around a ship. In his design, space contracts ahead of the vessel and expands behind it, carrying the ship forward inside a bubble of curved geometry. The ship itself would never move faster than light, only ride within a wave of shifting space. It was a clever solution on paper. Building one remains another matter entirely. Somewhere, dust drifts through a beam of dim light, each speck turning without hurry, going nowhere in particular. Notice how your breath moves in that same unforced way, rising and settling, like the hushed suspension of motes in air. Your shoulders can loosen now, following that same slow drift downward, heavier, looser. There is only this, the dust turning, the breath turning, the body sinking a little further into the dark. Let it carry you down, without effort, into sleep. Warp drive, as imagined mathematically, would require something never detected in nature: negative energy density, a kind of energy that pushes rather than pulls. Ordinary matter cannot produce it. Only strange, theoretical states, glimpsed briefly in quantum experiments, hint that anything like it might exist at all. Whether it could ever be gathered in the amounts needed remains unknown. The warp bubble stays, for now, a beautiful equation without fuel. Clocks aboard a ship moving near the speed of light tick slower than clocks left behind on Earth. This effect, called time dilation, has been measured directly using atomic clocks flown on airplanes and satellites. A traveler journeying near light speed for what feels like a few years might return to find decades, even centuries, have passed at home. Time itself bends around velocity. The faster the journey, the wider the gap between the traveler's years and the years of everyone left waiting. A civilization spread across many light years would wait years, sometimes lifetimes, for any single message to arrive. A question sent from one star system might not reach another for a decade. Its answer, traveling the same distance back, would take just as long again. Conversations would stretch across generations rather than minutes. Anyone ruling a civilization this wide could never speak with its edges in real time. NASA's New Horizons probe, after its historic flyby of Pluto in 2015, sent its first images home across a gap that took over 9 hours to cross. Traveling at the speed of light, that signal still needed most of a working day just to reach Earth's antennas. Pluto is, by cosmic measures, practically next door. A message from the far edge of the galaxy would take tens of thousands of years to arrive, if it ever did. Any empire attempting to govern the entire galaxy would face delays measured not in hours, but in millennia. A decree issued from a central capital might take tens of thousands of years merely to reach its farthest colonies. By the time a reply returned, the civilization that sent the original message might have changed beyond recognition. Governing at galactic scale would mean accepting that no single mind could ever hold the whole empire in the present moment. Our entire solar system circles the galaxy's center once every 225 million years, a single loop astronomers call a galactic year. Dinosaurs still walk the Earth, the last time our sun stood, where it now stands in orbit. Everything you have ever known, every human life, every empire on Earth has unfolded within one small arc of that vast circling path. The galaxy turns slowly, and we ride along without feeling it move. Reaching every star in the galaxy with slow sublight ships would still be achievable, given enough patience across generations. Even crawling along at a modest fraction of light speed, a fleet of colony ships could spread outward star by star, settling one system before pushing on to the next. Mathematically, filling the galaxy this way might take only a few million years. Against the galaxy's much longer age, that stretch of time is almost brief. A different strategy could colonize far faster than any fleet of crewed ships ever could. Instead of sending settlers, a civilization might send machines that build copies of themselves at each new star they reach. Each new probe would then launch further copies outward, doubling the frontier again and again. Growth like this does not creep, it multiplies, spreading not in a line, but in an ever-widening bloom across the stars. These machines are called von Neumann probes, named for the mathematician who first described the logic behind self-replication. Such a probe would arrive at a star system, mine local asteroids or moons for raw material, and use that material to construct new probes identical to itself. No fuel or parts would need to travel from home. The frontier would simply build its own future out of whatever raw stone and metal it finds waiting. Run the numbers on this kind of exponential spread, and the results become almost startling in their speed. A wave of self-replicating probes, doubling their reach at each new star, could sweep from one edge of the galaxy to the other in under 10 million years. That is a blink. Cosmically speaking, it suggests that any civilization willing to build such machines could, in principle, claim the whole galaxy remarkably quickly. Let your jaw loosen now, just slightly, as though it had been holding something all day. Let it release. Feel your eyelids grow heavier, thick, as though drawn down by their own weight. There is no need to keep your eyes closed on purpose. They simply rest there now, on their own. Behind them, the dark is wide and unmarked, like a room with no walls. Let your face grow still, unwatched, unwatching, simply here. 10 million years. The time such a wave might take to cross the galaxy sounds immense until placed beside the galaxy's own age. The galaxy has existed for roughly 13 billion years, meaning 10 million years is only a tiny fraction of that span, less than 1 part in 1,000. If even one civilization had started this kind of expansion early on, it would have had ample time again and again to finish the job. That mismatch between how quickly a galaxy could be filled and how empty it appears sits at the heart of a puzzle physicists call the Fermi paradox. Given billions of years and countless stars, expansion this fast should have happened many times over by now. Signs of such empires, radio noise, engineered structures, waste heat from vast machinery, should be scattered everywhere we look. Instead, the night sky remains remarkably, persistently quiet. One proposed answer suggests that some invisible barrier stands between simple life and galaxy, spanning civilization. Researchers call this idea the Great Filter, a stage so difficult to pass that almost nothing gets through it. It might sit early, in the leap from chemistry to life itself, or later, in the leap from clever tool users to something that survives its own technology. No one yet knows which stage, if any, is the true bottleneck. Another idea offers a gentler explanation, one that requires no filter at all. The Great Silence hypothesis proposes that advanced civilizations might simply choose restraint, deliberately avoiding the loud, visible expansion we might expect. A species that expanded without limit could exhaust its resources or provoke unknown risks. Staying quiet, staying small, might be the wiser, longer path. The stillness above us could be a choice, not an absence. A darker answer to this silence comes from an idea known as the dark forest hypothesis. It suggests that civilizations stay hidden, not from indifference but from caution, aware that revealing themselves might invite danger from others far stronger. In a galaxy where no one knows who else is listening, silence becomes a survival strategy. Every bright signal risks becoming a beacon. So the wisest presence, in this view, might be the one nobody notices at all. Life itself, according to an older idea, might already be a traveler. Panspermia theory proposes that life, or the simple chemical pieces that build it, could drift between stars, carried on comets, dust, or rock flung loose by ancient collisions. Under this notion, Earth's earliest ingredients might not have started here at all. Frozen microbes or organic molecules could survive long stretches of vacuum, arriving quietly, seeding new worlds without any intention behind the journey. A stranger version of that idea adds intention to the drifting. Directed panspermia imagines a civilization deliberately sending life, or its building blocks, toward distant stars as a slow, patient act of colonization. Rather than starships full of travelers, small capsules of microbes or genetic material would do the work, quietly seeding worlds across unimaginable spans of time. It is a plan with no rush, no report needed, no traveler expecting to see the result. Beneath every version of a galactic empire lies one unavoidable requirement. To truly govern across such distances, a civilization would need to solve either faster than light travel or faster than light communication, or find some way around needing either. Without one of these, an empire spanning many star systems could send ships and messages, but never rule in real time. Distance itself would always be the deciding authority, older and stronger than any throne. Physics has imagined a shortcut, though never confirmed one. Tachyons are hypothetical particles proposed to travel faster than light, born from equations rather than observation. No detector has ever caught one, and no experiment has found evidence they exist outside theory. They remain a mathematical possibility, a placeholder for a rule the universe may simply not allow. For now, tachyons stay exactly where they began, on paper in quiet speculation. Quantum entanglement often sounds like the answer everyone hopes for, yet it isn't one. Two entangled particles can respond to each other instantly, regardless of distance, but no usable information travels between them faster than light. Measuring one only reveals a correlation, not a message. Physicists have shown, again and again, that this strange connection cannot carry a signal. The universe keeps its speed limit intact, even at its strangest corners. Let your breath slow now, without any effort behind it. Notice the inhale arriving on its own, and the exhale lingering a little longer each time, unhurried, unbothered by the hour. There is no pace to keep, only this rhythm, older than any thought, older than any name you carry. Let each breath grow longer than the last, drifting further from waking, closer to rest, closer to the dark and easy quiet of sleep. No known law of physics allows a message to cross galactic distances instantly. Radio waves, light, even gravitational ripples all travel at the same fixed speed, stretching a single greeting into years or centuries of waiting. A ruler on one side of the galaxy could send an order and simply never live to hear the reply. Distance, in this universe, always collects its toll in time. A handful of theorists look toward gravity itself for an answer. Quantum gravity, the still unfinished attempt to merge gravity with quantum mechanics, might one day reveal exotic shortcuts through space-time, though nothing like this has been confirmed. The mathematics remains incomplete, the effects untested, the shortcuts unproven. It stays an idea at the edge of physics, tantalizing precisely because it hasn't been ruled out, and precisely because it hasn't been shown true. Perhaps a galaxy-spanning empire wouldn't need a ruler at all. Autonomous artificial intelligence could govern distant colonies directly, applying consistent law without waiting years for instructions from a distant capital. Each outpost could carry its own patient, tireless administrator, adjusting to local needs while still following a shared underlying purpose. Distance would no longer be a delay to manage, only a space the system quietly, steadily filled with its own judgment. Superintelligence has been proposed as one answer to the governance lag between stars. A mind vast enough and fast enough could hold the full weight of imperial law within itself, without needing to send anything anywhere. It would not tire, would not forget, would not misplace a decree somewhere between one star and the next. Such a mind, if it ever existed, would carry the empire inside its own thinking, rather than across its distances. A system built this way could enforce the same law everywhere, all at once, without waiting on orders from a distant capital. Each colony would answer to a presence already there, already deciding, already adjusting to whatever the moment required. Nothing would need to travel except the outcome. Rule, in this arrangement, would not spread outward from a throne, but exist everywhere at the same time, folded quietly into the machinery of each world. History already shows what happens when governance cannot keep pace with distance. Rome strained under the cost of moving orders, soldiers, and grain across its own provinces. The Mongol Khanates splintered once. Messengers could no longer outrun the empire's own size. Communication delay was rarely the whole cause of a collapse, but it was almost always part of the strain, a slow erosion beneath every larger crisis. A true galaxy, spanning empire might face this same strain magnified across light years instead of provinces. Star clusters far enough apart could drift into their own customs, their own laws, their own quiet sense of belonging to something separate. What began as a single order might become many small ones, connected mostly by memory and old records. Distance has a way of turning one story into several, whether the map admits it or not. Isolation of this depth could also work on the body, not just the culture. Across thousands of generations, colonies cut off from Earth might drift genetically, shaped by different gravity, different light, different air. Small differences would accumulate the way sediment settles, unnoticed year to year, unmistakable after enough time has passed. A population once identical to its ancestors could, given enough isolated centuries, become something else without anyone deciding it should. Long enough separation might carry this further than culture or appearance. Biologists studying isolated populations on Earth already see how distinct environments and generations apart can nudge a species toward divergence. Applied to true interstellar isolation, this suggests something stranger still. Colonies descended from Earth humans, evolving under alien skies, might eventually become a different branch of the same old tree, related but no longer quite the same. An economy vast enough to span a galaxy would likely need wealth measured differently than gold or grain. Antimatter, capable of releasing enormous energy from a small amount of mass, has been proposed as one such currency. Exotic matter, theorized but never observed, might serve a similar purpose if it exists at all. In an empire built on stars rather than soil, value might be counted in energy density rather than land. Let your attention travel down through the body now, noticing where it rests against the mattress. Feel the heaviness settle first into your shoulders, then your arms, then your hands, each part growing dense and unwilling to move. Your legs follow, heavier still, sinking a little further with every breath. There is no need to hold any of this weight yourself tonight. Let the bed carry it, all of it, while you simply rest inside your own stillness. Long before any empire could reach beyond the solar system, it might begin much closer to home. Asteroid mining is proposed as an early step toward economies built on space rather than land. Metals rarer on Earth exist in abundance among certain asteroids, waiting without urgency for retrieval. A small robotic craft, patiently working its way through rock and ice, could mark the first quiet foothold of something much larger. Beneath the moon's dust lies a resource. Some hope could power that larger future. Helium-3, delivered over billions of years by solar wind, is proposed as an ideal fuel for nuclear fusion, cleaner and more efficient than the isotopes used on Earth. None has yet been mined or burned this way. It waits there still, scattered thin across a silent gray surface, a possible fuel for journeys not yet begun. Encasing a star whole may be less practical than surrounding it with countless smaller pieces. A Dyson swarm imagines thousands of solar collectors, mirrors, and habitats orbiting in loose formation rather than one solid shell. Each piece captures a fraction of the star's light, adding together towards something like a Dyson sphere's total harvest. Engineers favor this design because it avoids the structural strain a single enclosing shell would face. Such a swarm need not appear all at once. One collector could build another, using local material and solar power to assemble the next piece without waiting for instructions from home. Over centuries, this quiet multiplication could grow a scattering of panels into a vast structure. No single launch, no single decade, only a slow accumulation, guided by machines that never tire of the work. Not every megastructure is meant to stay in place. Certain theorists have proposed stellar engines, structures capable of nudging an entire star system through the galaxy over immense stretches of time. The idea sounds impossible until measured in patience rather than force. A star moved a hair's breadth each year could, after enough millennia, drift a meaningful distance across the galactic disk. A Shkadov thruster is one imagined design for that kind of movement. It proposes a colossal mirror positioned beside a star, reflecting radiation in one direction, and, through the pressure of that light, easing the star itself very gradually the other way. No metal has ever been bent for this purpose. It remains a diagram, an equation, a shape drawn only in the mind of physics. Beyond ordinary stars, certain thinkers look toward black holes as engines built for the very long term. A black hole offers a gravitational furnace with no fuel to exhaust, no light to dim, only mass-curving space in a way that could, in theory, be tapped for power across ages longer than any star's life. It is an idea that reaches past our present understanding of engineering entirely. Hawking radiation, first described by physicist Stephen Hawking, suggests that even black holes slowly lose mass, releasing faint radiation as they do. A small enough black hole might, in theory, be surrounded and harvested, its dwindling mass converted steadily into usable energy. The smaller the object, the faster this radiation. No civilization has built such a device, but the physics permits the dream to be drawn out on paper. Habitats need not resemble any moon or planet at all. Some designs imagine long rotating cylinders, spinning steadily to create the sensation of gravity along their inner walls. Inside, forests, rivers, and open sky, painted by curved windows, could exist entirely apart from any world surface. The idea trades solid ground for engineered motion, gravity manufactured rather than inherited. Gerard O'Neill, a physicist working in the 1970s, gave this rotating design its clearest form and its name. He proposed enormous cylindrical colonies, paired and counterspinning for balance, large enough to house entire small cities. His sketches showed clouds forming inside artificial skies and sunlight arriving through mirrored panels. The concept remains unbuilt, yet it still shapes how many imagine humanity's first true homes beyond Earth. Somewhere far off, a low hum rises and fades, the kind of sound a house makes when it settles into the night. It arrives without asking anything of you, and it leaves the same way, unhurried, indifferent to whether you notice. Let your breathing follow that same rhythm, rising, pausing, falling away. There is no message in the sound, no task waiting inside it. It simply passes, and you can let it carry a little more of your wakefulness with it, each time it fades. A star's entire output, in some imaginings, could feed something far stranger than a colony. A matryoshka brain proposes nested layers of computing structures built around a star, each shell catching the waste heat of the one before it. Named for the nesting dolls it resembles, the design imagines a civilization converting nearly all of a star's energy into vast, silent computation. No such structure has ever been observed, only theorized as a distant horizon of possibility. A galaxy need not hold only one empire at a time. Some theorists propose that vast distances could let several spacefaring powers rise and spread without ever meeting. Each might claim its own arm of stars, unaware the other exists. The scale involved is wide enough for these separate histories to unfold side by side, never touching, never colliding, each certain it stands alone among the stars. Resource competition among spacefaring civilizations could ignite conflict between them. Two expanding powers might one day reach for the same star system, the same reserve of ice or metal. Growth models suggest friction, not malice, could spark such encounters as colonies seek room to grow. Historians studying earthly wars note that resource pressure has driven more conflict than ideology ever did, a pattern that some worry might repeat again among the stars. Relativistic weapons, hurled at near light speed, count among the most severe theoretical threats a civilization could face. A projectile moving that fast needs no explosive charge, its velocity alone supplies the destruction. Physicists studying interstellar defense scenarios describe these weapons as nearly impossible to detect in advance. No warning could arrive before impact, since the object would outrun any signal announcing it. The concept remains entirely hypothetical, a boundary marking what physics allows. A relativistic kill vehicle could destroy a planet using nothing but kinetic energy. A mass no larger than a grain of sand, accelerated near light speed, could release energy rivaling the largest nuclear detonations on impact. No warhead is needed, only velocity. The physics behind it is simple, though reaching such speeds remains far beyond current technology. It endures more as a thought experiment than a plan, a reminder of how strange energy becomes near light speed. Advanced civilizations might destroy themselves before ever reaching galactic scale. One line of thought holds that technological growth can outpace the wisdom needed to manage it. A species might gain the power to reach other stars at nearly the same moment it gains the power to end itself. If this pattern were common, it could explain why the galaxy appears so still. The idea offers no proof, only a possible answer folded inside a long cosmic silence. Nuclear war stands among the most often cited barriers in the Great Filter idea. Weapons capable of ending civilization arrived on Earth only decades after radio waves first reached beyond it. Analysts studying this concept often point to nuclear conflict as a threshold every technological species might eventually face. Passing through it seems to require restraint as much as capability. Earth crossed this threshold and continued onward, still counted among the civilizations that made it through. Ecological collapse offers another candidate for that same filter. A civilization's own success can undermine the world sustaining it. Overuse of land, water, and atmosphere might erode a planet's capacity for advanced life long before any single disaster strikes. Ecologists studying long-term sustainability describe this as a slower filter than war, measured in decades rather than moments. Whether Earth passes through it safely remains an open question, still being written by every generation that follows. Life itself, in one view, may be the rarest accident in the cosmos. Beyond filters of war and collapse lies a deeper question, whether biology ever begins at all. Certain theorists argue that the chemistry needed to spark life depends on so many coincidences that it may rarely repeat elsewhere. Under this view, the universe could hold countless barren worlds for every living one. The idea shifts the mystery of cosmic silence from technology back toward chemistry itself. The rare Earth hypothesis names a long list of improbable conditions our planet happened to meet. Proponents point to a stable star, a large moon, a shielding neighboring giant, and plate tectonics working together across billions of years. Each condition alone seems reasonable, yet their combination together might be exceptionally uncommon. If true, complex life like our own could remain rare even among worlds that harbor simple microbes. The hypothesis remains debated, one attempt among many to weigh our planet's true rarity. Let a warmth begin somewhere small, perhaps behind your eyes, perhaps low in your chest, and let it spread from there without hurry. Feel it move into your shoulders, loosening what the day left tightened there. Let it drift down through your arms, into your hands, until your fingers rest heavy and still. Let it pool in your stomach, your hips, your thighs, sinking a little further with each breath. By the time it reaches your feet, you may already be half asleep, carried along by nothing but this spreading warmth. Plate tectonics may play a hidden role in keeping a biosphere alive across billions of years. Shifting plates recycle carbon between crust and atmosphere, helping stabilize temperature over long stretches of time. Without this slow churning, a world's climate could drift toward extremes unsuited to complex life. Geologists studying other rocky planets note how rare this exact balance of internal heat and crust movement might be. Earth's restless ground, it seems, has been working in our favor the whole while. A companion in the sky may have done more for us than light alone. Earth's moon, unusually large for a planet its size, exerts a steady gravitational pull that keeps our axial tilt from wandering. That steadiness allows seasons to remain mild and predictable rather than chaotic. Astronomers modeling moonless worlds find their tilts can swing wildly over time, disrupting climate patterns. Our companion, drifting nearby each night, may be a quiet architect of stability. Far beyond Earth's orbit, a giant world may stand as an unseen guardian. Jupiter's immense gravity is thought to capture or deflect many comets and asteroids that might otherwise cross paths with Earth. Simulations suggest that without such a massive neighbor, impact frequency could rise considerably. This protective role remains debated among planetary scientists, since some models show Jupiter also flings danger our way at times. Still, its presence seems to matter more than mere distance would suggest. Our own Sun, so familiar, may itself be an unusual kind of star. It burns with a steadiness many Sun-like stars lack, avoiding the violent flares and eruptions common elsewhere. Astronomers surveying nearby stars have found many far more volatile, prone to radiation bursts that could strip a young planet's atmosphere. This calm, dependable output may be one more quiet condition life needed to take hold. The Sun's gentle constancy, in this light, feels less ordinary than it once seemed. Across vast reaches of space, a single burst of energy could erase life before it ever begins. Gamma-ray bursts, among the most energetic events known, may periodically sweep through regions of a galaxy, stripping away protective atmospheres light years away. Astrophysicists estimate such events could sterilize entire stretches of a galactic disk over cosmic timescales. Whether Earth has ever brushed close to one remains uncertain, buried in a past too distant to fully read. The galaxy, it seems, carries occasional storms of its own. Not every corner of the galaxy may welcome life equally. The galactic habitable zone describes a band of distance from the core where radiation is mild enough and heavy elements plentiful enough for planets like ours to form and endure. Too close to the center, radiation grows fierce. Too far toward the edge, the raw materials for rocky worlds grow scarce. This concept narrows the search for life to a modest ring within the galaxy's vast spiral. Earth, fittingly, sits comfortably within it. Near the galactic center, conditions turn far less gentle. Dense star clusters there churn with radiation, frequent supernovae, and gravitational disturbances that could scatter planets from stable orbits. Astronomers modeling this crowded region find it difficult for a world to remain undisturbed long enough for complex life to develop. The core burns bright and beautiful from a distance, yet its brilliance may come at the cost of habitability. Life, it appears, favors the quieter outskirts of a galaxy's grand structure. Long before telescopes searched for real evidence, storytellers had already imagined empires among the stars. Writers across the 20th century used the shape of a galactic empire to explore ideas about power, distance, and time. These fictional worlds let audiences consider questions too large for ordinary history. Stretched across centuries and star systems, the device offered a mirror for humanity's own ambitions, magnified to a cosmic scale. Fiction, in this way, became a kind of thought experiment for the sciences to later examine. Isaac Asimov once built an entire universe around the slow decline of a galactic empire. His Foundation series imagined a civilization spanning millions of worlds, gradually crumbling under its own vastness. Within that story, a scholar develops psychohistory, a mathematics meant to predict the rise and fall of societies. The tale reflects real historical patterns of overextension and collapse, scaled up to galactic proportions. Asimov's imagined empire remains one of fiction's most enduring meditations on the fragility of scale. Asimov's psychohistory imagined something remarkable, that the fate of trillions could be forecast through mathematics alone. In his stories, patterns of human behavior, multiplied across vast populations, become predictable in aggregate, much like gas particles obeying physical laws. Real historians and statisticians have questioned whether human societies could ever be modeled with such precision. Yet the notion continues to intrigue those studying complex systems and collective behavior. It remains a compelling fiction, standing at the edge of what mathematics might one day attempt. Let the mind settle like dust, drifting through a shaft of still air, each grain catching light before it disappears into the dark below. There is no need to follow any single speck. Let them fall as they will, unhurried, forming no pattern, asking nothing of you. Your breath can move at its own pace now, slower than thought, slower than worry. The room around you holds still, and so, gradually, do you. Frank Herbert imagined an empire built on a single, irreplaceable resource. In his novel Dune, noble houses ruled scattered planets under a feudal galactic order, all of it dependent on a rare substance called spice, mined from one harsh desert world. Control of that resource meant control of travel, trade, and prophecy itself. Herbert's empire reads less like science fiction and more like an old trading empire, dressed in robes of sand and starlight. A phrase entered everyday language through the light of a movie screen. George Lucas's Star Wars gave the world the term Galactic Empire, complete with dark uniforms, distant senates, and a single looming figure, cloaked in menace. Audiences absorbed the phrase so completely that it became shorthand for any vast, centralized power spanning the stars. Before Lucas, empire suggested Rome or Britain. After him, it suggested something built entirely of imagination. Elsewhere in television history, Star Trek offered a gentler alternative to empire altogether. Its united federation of planets joined worlds through voluntary alliance rather than conquest, governed by shared principles instead of a single throne. The contrast was deliberate. Where empire implies command from a center, federation implies conversation among equals. Two visions of the future, born in the same decades, imagined very different ways for civilizations to share a galaxy. Fictional empires, again and again, borrow their shape from history already written on Earth. Writers reach for familiar patterns of conquest, taxation, and rebellion, then stretch them across galaxies instead of continents. A distant emperor mirrors a distant king. A frontier colony mirrors a frontier province. The stars simply provide a larger canvas for questions humanity has been asking about power since long before telescopes existed. Space agencies have taken the idea of the generation ship seriously enough to study it as more than fiction. Engineers and planners have modeled vessels that would carry entire communities across centuries, with children born, raised, and aged before any destination is reached. These thought experiments explore closed ecosystems, social stability, and the psychology of populations who will never see the world their ancestors left. The ship itself becomes a slow-moving civilization. 100 years was the horizon chosen for an unusual research effort. NASA's 100-year Starship project explored what interstellar travel might require by the year 2100, gathering physicists, engineers, and social scientists to consider propulsion, life support, and governance across such a voyage. The project produced no spacecraft, only groundwork, a patient inventory of what remains unsolved before humanity could ever leave for another star. A galaxy of scattered colonies might eventually need one shared tongue to hold itself together. Communication across light years already strains coordination, and language drifting apart on isolated worlds could deepen that distance further. Some proposals imagine a standardized language maintained deliberately, much like trade languages once bridged ancient empires on Earth. Without such an effort, distant colonies might simply grow into strangers who happen to share an origin. Across thousands of years, language and custom drift apart, even without any distance at all separating people. Add centuries of travel time and no shared news between worlds, and colonies could evolve entirely distinct dialects, holidays, and beliefs. A message sent from one settlement might arrive at another, already outdated by generations. What began as one people sharing one history could slowly become many peoples sharing only a distant memory of home. Ships, traveling near the speed of light, would carry their passengers into different rivers of time. Relativity means that years aboard a fast-moving vessel could correspond to decades or centuries back on the worlds they left. A colony founded by travelers might, from their own perspective, be brand new, even as its inhabitants on the ground have aged through many lifetimes. Any empire spanning such journeys would hold within it colonies living in entirely different subjective eras, side by side, yet never quite in step. Simultaneity itself might bend beneath an empire spread across the stars. Relativity teaches that two events judged simultaneous by one observer may unfold in a different order for another, depending on speed and position. A ruler moving between star systems and a subject remaining still would each carry a valid but different sense of now. What counts as the same moment might dissolve into many overlapping moments, none of them wrong. Let your face rest now, the way still water settles. Let the jaw loosen, the brow smooth, the small muscles around the eyes forget their work. Behind closed lids, there is only a warm, low, dark, unhurried, and without edges. Let the weight of your eyelids feel like the only weight in the room. Whatever the mind was holding, let it slip from the hands of your face and rest there a while longer. Neutron stars, crushed remnants of dying suns, have been proposed as extreme resources for advanced engineering. Their gravity and magnetic fields are unlike anything found on any planet, and theorists have imagined harvesting that intensity for energy or even for exotic forms of computation. Matter falling towards such a star releases enormous power. No civilization has attempted this, but the physics of these objects makes the idea at least imaginable. Pulsars sweep their beams across the galaxy with a steadiness rivaling atomic clocks. Their rotation is so regular that engineers have proposed using pulsar timing as a kind of cosmic lighthouse system, letting distant travelers calculate their position by comparing signal patterns. NASA has already included pulsar maps on spacecraft meant to outlive human memory. A galaxy-spanning empire might navigate not by stars alone, but by these patient, ticking beacons. When pulsars were first detected in 1967, their signal was so precise that astronomers briefly wondered if it might be artificial. The regularity seemed almost too perfect for a natural object, and the discovery was informally labeled with a name suggesting little green visitors. Further study soon revealed the true cause: a rapidly spinning neutron star sweeping a beam like a cosmic lighthouse. The mystery resolved gently into something no less remarkable for being natural. On a summer evening in 1977, a radio telescope in Ohio recorded a burst of signal so strong that an astronomer circled it in red pen and wrote "Wow" beside the printout. The signal lasted about 72 seconds and matched no known natural source, yet it never repeated despite decades of searching the same patch of sky. It remains unexplained, neither confirmed as artificial nor fully understood as natural. If a distant civilization altered its own atmosphere, the way industry has altered Earth's, that change might be detectable from light years away. Astronomers have proposed searching for chemical signatures, such as certain industrial gases, mixed into a planet's air, evidence not of biology, but of technology. Such technosignatures would be indirect and easily confused with natural chemistry. Still, the idea offers one more careful thread to search among starlight. Several survey projects have quietly scanned the sky for stars radiating unusual amounts of infrared light, the kind that might result from a colossal structure encircling a star and re-radiating captured energy as heat. Catalogs of millions of stars have been searched this way, looking for glowing outliers. None have yet matched the signature such a megastructure would produce. The search continues without urgency, one patient survey after another. Oxygen and methane, when found together in an atmosphere, tend not to last long without something actively replenishing them. On Earth, that something is life. Astronomers studying exoplanet atmospheres look for these gases as gentle clues rather than proof, knowing chemistry alone can sometimes mimic biology's fingerprints. A single balanced breath of gases, glimpsed across trillions of miles, might one day suggest a living world without ever confirming it outright. In 2015, a star catalogued by researcher Tabitha Boyajian dimmed in patterns no known planet or dust cloud seemed to explain, sometimes losing as much as 20% of its light unevenly. For a brief season, some proposed the strange dimming might come from an enormous structure under construction, partially blocking starlight as it grew. The idea captured public imagination even as astronomers treated it as only one hypothesis among several, patiently awaiting more data. Follow-up observations of that same star eventually favored a quieter explanation: uneven clouds of dust and debris, perhaps the remnants of a shattered moon or comet swarm, could account for the strange dimming without invoking any structure at all. Astronomers who once wondered about megastructures largely set that idea aside. Nature, it turned out, had its own ways of casting irregular shadows across starlight. A number of thinkers now question whether a true galactic empire could ever exist at all. Distances measured in tens of thousands of light-years, they argue, may simply be too vast for any central authority to hold together. Physics itself, not politics, might be the limiting factor. Under this view, the very geometry of the galaxy quietly forbids the kind of dominion history's empires once achieved on a single world. Let your breathing find its own long shape now, in through the nose, and out even longer than it came in. Each exhale can trail a little further than the last, like a wave settling back from shore. There is no rhythm to chase, only the one already moving through you. Let the next breath arrive on its own, and the one after that, unbothered by counting. Not every thinker believes empire is the natural shape for a spacefaring people. Loose federations, voluntary and lightly connected, might survive interstellar distances far better than any centralized rule ever could. Without a capital city commanding obedience across thousands of years of delay, colonies might simply choose cooperation over control. Independence, in this telling, becomes the price of surviving the dark between stars. Another model imagines expansion at only a fraction of light speed, stretched across countless generations. Colony ships would leave one star, settle, grow, and send out daughter ships centuries later, spreading outward like roots through soil. No single voyage would seem remarkable. Only the accumulated span of ages would reveal the shape of something vast quietly taking form. Even at such unhurried pace, the outcome could still be remarkable. Given enough time, a civilization crawling outward star by star might eventually touch most of the galaxy's habitable reaches. Millions of years feel immense to a single life, yet the galaxy has stood for billions. What seems impossibly slow to us might simply be ordinary, viewed from time's much larger scale. Beyond our own galaxy lies a staggering abundance of others. Deep surveys of the sky suggest the observable universe holds roughly 2 trillion galaxies, each containing its own hundreds of billions of stars. Our Milky Way, vast as it feels, is only one modest neighborhood among an ocean of neighborhoods. The night sky, dark to the naked eye, is in truth crowded beyond imagining. Reaching beyond the Milky Way would mean confronting distances almost impossible to compare with anything familiar. The nearest large galaxy sits millions of light-years away, thousands of times farther than the stars within our own galactic neighborhood. Any journey between galaxies would dwarf even the longest imagined interstellar voyage. Empire, at that scale, would need to mean something entirely different than it ever has before. Space itself is stretching, and the farther a galaxy sits from us, the faster it appears to recede. This gentle pressure, attributed to what cosmologists call dark energy, is slowly widening the gaps between galactic clusters. Light that could reach a neighboring galaxy today may never arrive if sent much later. The universe, in its own unhurried way, is quietly closing doors behind itself. Cosmologists estimate that within about 100 billion years, most galaxies visible today will have drifted beyond any possible reach. Their light will fade past the horizon of what any traveler, no matter how patient, could ever cross. The universe will not end, but it will become quieter, each galaxy more alone within its own shrinking pocket of reachable space. Time, in this telling, is also a border. Expansion, if it ever happens, may be a window rather than a permanent door. Any civilization hoping to claim distant galaxies would need to act before the widening gaps outrun its ships. Wait too long, and the cosmos itself withdraws the invitation. Reaching outward, in this framing, becomes a matter of timing as much as ambition. The galaxy stays within grasp only for a while. Far beyond any empire's timeline lies the heat death of the universe, a state physicists place almost unimaginably far in the future. Stars will exhaust their fuel, galaxies will darken, and even matter itself may eventually dissolve into faint, diffuse radiation. The number of years involved dwarfs the age of the universe so far, many times over. Against that horizon, every empire, however vast, would be a brief flicker. Whatever shape a galactic empire might take, current physics still holds one boundary firm. Nothing with mass can outrun light, and no signal can outpace it either. Any dominion spanning the stars would have to live inside that limit, stretching patience across centuries instead of bending the law itself. Vast reach, it seems, would always come paired with vast waiting. Let your body grow heavy now, one part at a time. Feel your feet settle deeper into the mattress, then your legs, loose and unmoving. Let that heaviness climb into your hips, your back pressing down like something finally allowed to rest. Your shoulders sink next, then your arms, your hands going still and full. Even your head feels weighted now, cradled, sinking a little further with each breath you release. For all this reach of imagination, humanity's own ships have gone only a short distance. No crewed mission has yet traveled beyond the moon's orbit since the last Apollo flights returned home. Every astronaut since has stayed within a narrow band close to Earth. The galaxy waits untouched by human hands, while our farthest footsteps remain just beyond our own front porch. Whether any true galactic empire could ever exist remains open, unresolved by physics or philosophy. Perhaps light speed limits make it impossible. Perhaps patience, automation, or some undiscovered principle could make it real after all. No one yet knows which future awaits, or whether the question will matter to whoever asks it next. And so the story of empire, out among the stars, is still unwritten. Rest well tonight, under a sky still full of unanswered distances. Good night.